Hi everybody. I continue the first lecture of the general chemistry for medical students. Today I want to continue with the atomic mass. As you know, in the periodic table, the hydrogen is the first element. Okay? And it has the smallest atomic mass. And the mass of the hydrogen is with the one proton and the one electron, because hydrogen hasn't neutron. It has around 1.6 multiplied 10 power minus 27 kilogram. Okay? Okay? As you see here, it is a very small number, okay, which we can use in the chemistry and in the calculation, okay? And it is hard, for example, if I want to say I have a 5 atom hydrogen or I have a 2 mole hydrogen, and I cannot calculate easily the relation of the atomic mass and the other properties, for example, for the concentration and for the finding of the mole. For this system, we choose unit for the atomic mass. 1 unit for the atomic mass is equal, okay, 1 over 12, okay, mass of carbon 12 isotope, okay? As you see here, it is our unit. For example, in this case, we can easily calculate, for example, carbon 12, 1 over 12 is 1 unit. For example, hydrogen, it is a 1 unit. And the relative atomic mass of the hydrogen is equal 1 unit. Okay? And it will be the base level of the atomic mass. Okay? And the sum of the relative atomic mass is relative molecular mass. For example, if I have a hydrogen, it is 1, and oxygen, it is a 16. For the water, I can calculate 2 times 1 plus 1 times 16. It is 18 gram per mole. It is a unit of the which can be used for the molar mass and the molecular mass. And in this case, it is easy. Why we can use carbon 12? Because the carbon 12 has a 6 proton and 6 neutron. Okay? And the isotope mass is exactly equal to 12. Okay? But the other, for example, carbon 13, okay, isotope mass equals 13.003, okay, it's not exactly 13, and it is not good for the calculation of the mole atomic mass. And the other things we have to care about this now is very easy from here. For example, I have a water, okay, 1 mole of the water, okay, is equal 18 gram, because as you see here, the molar mass is the 18 gram per mole. Then 1 mole of the water is equal 18 gram. And 1 mole of the water has 6.022 multiplied 10 power 23 number of the molecule of the water. Of water. Okay? And because every molecule of the water has 3 atoms, if we multiply this for the 3, okay, is equal around 6, okay, around 0.6 multiply 10 power 24 atoms. Then 1 mole of the water equals this amount of the atoms. Okay? This number is the Avogadro number. This number called is Avogadro number. We can calculate the number of the particle. Okay? Excuse me, I wrote Avogadro number. We can use the calculation of the number of the particles, okay, in 1 mole. Or we can say 18 grams of the water has this amount of the molecule. Okay? It's very easy and we can calculate this very. With this situation, in this situation, we can write very easy formula is N equal M per big M. N is the amount of the mole and M is the mass, unit is the gram, and M big M is the relative molar mass, relative molar mass, and the unit is gram per mole. Okay? And we can calculate the mole, and from the mole we can calculate the amount of the molecular atom. Okay? After we can calculate the amount of the atom or molecule, we can also calculate the amount of the electron, proton, and neutron, because the water has, as you know, for example, oxygen has hydrogen has 1 proton. We have 2 proton here. Okay, and oxygen has 8 proton. It has 8 proton plus 2 is 10 proton. Okay, and we can, if we multiply this number in the 10, we can calculate the number of the proton in the molecule. It's very easy and very nice. Okay, and the unit of the molar mass, as I mentioned, it is a gram per mole. Okay. There are 2 models of the atoms which we can discuss. For example, as you remember in the last lecture, I mentioned for the electron we have theory with the name of the Thomson or Plumb-Podding theory. And we have a Rutherford theory which they explain about the theory of the atom. Okay, because we know the atom has two parts. The core is the core of atom. Okay, inside the core we have a neutron and a proton, and we have orbital surrounding the atom. This orbital we can find. As you know, the orbital is the place that we can find the electron. It is orbital of electron. Because we don't know the exact place of the electron. Electron is the rotate around the core, and we know the relative atomic mass is equal neutron plus proton, because the size of the electron is the 1 over 10,000. 10,000 is smaller than the proton and the neutron, and we can cancel in this formula to find. But we know the number of the neutron element, the number of the proton is equal to the number of the electron. Okay, it's very easy, and it's very easy. As I mentioned. Isotope also has the same number of the proton and the different number of the neutron, the same element, but the different number of the neutron. Okay. Also, I speak more about the problems with the Rutherford models. Okay. The first problem with the Rutherford models is about stability of the atoms. As you know, if we know, every element has a emission spectroscopy, emission spectrum or emission spectra, which when the light connected or contact with the atom, okay, and excited, and it emitted the light. This emission light has a different wavelengths and wavelengths and the frequency, and in this this theory is not accepted with the Rutherford theory. It is very easy and then very important. And the other thing, we have the other problem which cannot actually we cannot use the Rutherford theory. It is the milestone in the quantum mechanism, because we use the quantum theory in the physics, in the biophysics, in the physics mainly, as you remember, because there is a two type of the theory, the physics. We have a classical physics and the quantum physics. And the first, one of the scientists which is he mentioned about this quantum theory, it was Planck, because Planck used one formula which he said E equal Planck constant multiply frequency. Okay, it shows the relation of the energy of the particle, for example, electron inside the atoms. Okay, directly related to the frequency of that particle, and h is the Planck constant. Okay, the unit of the Planck constant is the joule second. Okay, it is, I think, around 6.6 multiplied 10 power 24, minus 24, I think. And the second scientist was Albert Einstein, which he mentioned about the electromagnetic wave and the photon, and we just I hear mention about this theory, and he said the speed of the energy has a relation with the speed of the light, and in the power 2. It is very important because it's also, this theory shows when we can calculate the energy of the particle with its speed. And if you also, the other theory say if we increase the speed to the speed of light, the whole of the matter can convert to the energy. It is one of the important things in the physics and chemistry. And I continue with the Bohr model of the atom, because in the Bohr model of the atom, we have what is very important in the Bohr model is the energy levels, because in the energy levels they say that every electrons, for example, in the atom has a different energy. Okay, because of it is depend for the type of the orbital and distance from the core, and these two measures is very important. The energy level of the particle can be different. Also, every particle, for example, electron, which is rotated around the core, the energy level can change because it can be the effect of the environment, or because of the effect of the core and the electrons. Because we, as you know from these two theories, okay, as I mentioned here, the frequency and the speed of the particle can affect in the energy, and it is very important when the energy change. Absolutely, the frequency also can change, also vice versa, or when the speed can change in the particle, and the energy also can change in the atom, or for example in the electrons or the atoms. Okay, I go now. In the physics mainly we will study about the emission spectrum, because in the energy spectrum we have a different layer of the energy, which I will show here. Okay, the energy level of can be different. Okay, because it is very is important for the emission spectrum also. Okay, every atom, okay, has a core and the orbitals. Okay, and there is a different level of the energy surrounded with by the center. Okay? And if it goes far from the core, the energy level will be goes up, and we will have a higher energy. Okay, and the first level of the here, it is as you see here, it has the highest energy because it's very close to the core. And for example, if you have a different layer of energy, for example, Lyman, Passion, and Balmar, because we say it is the first layer is the Lyman, and the second one Passion, and the third one is the Balmer. Balmer and the Passion, and the energy level is the difference from this level, and from this different energy level, and the possibility of the electron, where we can find the surrounded the core, we can mention about the orbital theory. Okay, many scientists speak about that, but the main, but Schrödinger and he spoke about this theory, and the famous Heisenberg uncertainty principle theory, which he mentioned, is one of the important theories in the quantum mechanism. Okay, and now I want to continue with the quantum number. We have 4 types of the quantum number. Okay, I will do here and I will mention here. Okay. Okay, there is a 4 types of the quantum number. The first one is the N, the second one is L, third one is the ML, and the fourth one is the MS. Okay, and from this theory number we can find the position and the place of the electron and the property of the electrons in surrounding the which is surrounded the atom. The first one is the N, is the principal quantum number. It is the numbers between 1, 2, 3, 4, and okay. Or we can use the alphabet K, L, M, N. Okay. Okay. It shows the principal quantum number shows the size of an orbital, and they are also shows the shell, and it shows us the energy of electron. But it is very important. We can calculate the energy of electron, as you remember from the Planck formula and Einstein formula. We can calculate the energy and the difference energy level with the principle of the quantum. It's very easy. And the second number, it is the angular quantum number. It is equal n minus 1. Then we can find L equal 0, 1, 2, 3. 0 is, or we can use S, P, D, F. Okay? This shows energy, but this shows, I say, the shape of the orbital. Because as you see here, we are in the first layer. We can find the energy of each layer, and also it is a shell. And inside the shell we can find the subshell. Here we can find they all are the shell. Okay? And here we can find the subshell. For example, the first layer is here 1. Okay? The name is the K. N is equal 1. Okay? L equal in this layer is the 0. Okay? The second layer is N is the 2. N is the 2. L is the 1 and the 2. And the third theory, which is important, and also this layer we can find in the subshell also we can calculate different energy. layer, because also some shell also has a different energy. For example, the S and the P, and the P is higher energy compared to the S. And the third one, we have a magnetic quantum number. Magnetic quantum number is between the minus L till plus L. Okay? For example, if we have a first layer, it is a 1. Okay? The L, or angular quantum number, is the 0, is S. And if we put a number between 0 to 0, it is 0. And I can draw here very easily. The first layer has just one orbital. The name is the S, or 0. Okay? And the number of ml is it has a 1 unit. Okay? And it shows the ml magnetic quantum number, the orientation and direction of orbital in the space. It shows orientation and the direction. Okay, in which direction we can find the orbital in the space. Is it spherical or other shapes we can find. And also, as you see here, in the every orbital the energy is the same. Then in the magnetic quantum number, we don't care about the energy of electron. The last one is the spin quantum number. Spin show in the one orbital we have a 2 spin plus half and the minus half, because they are exactly the same but in the different direction. Then I can draw here, one is up, one is the down, plus half and the minus half is the first line. For example, the second layer, okay, N is the 2, is L can be 1, and the formula I can write from here. N is equal to L equal 1, and ML is equal to minus 1, 0 until plus 1, or we can find a small 0. Okay? As you see here, in the second layer, we can find L is the one, is the name is the P, okay? We can say Px, Py, and Pz, okay? And it has a 6 electron, plus also we have a S, because as you see here, we have an 8 electron in the second layer. And in the third layer, okay, in the third layer, N is equal 3, L is equal 2, and ML is between minus 2 plus minus 2 minus 1, 0 plus 1 plus 2 is the 5, and also include this, the minus 1, 0 plus 1 and 0. In this case, we can have it in the third layer. We can have it 5. The name is in the here. N is the 3 is the M. The name is M, and here is the orbital name is the D. Here is the orbital name is the P. And in this case we have a 5 orbital. The name is the D. 10 electron can be inside it. Also we can have a P orbital, and we can have a S orbital. 10 plus 6 is 18. In this slide we have 18 electron. In this slide we have 18 electron. Here is we have 8 electron. And the first slide we have 2 electron. And the last one, N is equal 4. L equals 3. It is the name of orbital is the F. And it is between minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Okay, 7. Okay, if I do here, I can do here, F orbital, 7 number. And each has a 2 electron in each orbital. Plus, also we have the orbital, 10 number electron, p orbital with 6 electron, s orbital with 2 electron, 14, 20, 32 electron. In this line we have a 32 electron, as you see here. And when we use a periodic table, we start from the first slide. For example, hydrogen has just with orbital, just with 1 electron. Helium has the second electron. This orbital is the full, but the other four, we don't have other orbital. Other like shell is just we have 1 shell, and we have also 1 subshell. But if we go, for example, I use for example 1 electron is oxygen. For example, oxygen, the atomic number is 8. Okay? If you see the first 2 electrons, 1s2 with the first line is N, 2s2 in the second line, because we have a 1s and 1 p orbital and a 2p4. Okay? As you see here, it is the first shell and it is the second shell. In the first shell we have just s orbital with a 2 electron, and in the second shell we have s and the p electron. But the first shell is the full, but the second shell we have 8 electron, but we have here 6 electron. Then oxygen can have a 2 electron more. Okay, then it is unstable, and it can accept 2 electron and become then more stable. And because of this oxygen can accept 2 electron or donate or share 2 electron. Is depend for the reaction and depend for the compounds. Whether it is ionic or it is for example molecular or covalent bond. The other things I spoke. The other rule is the Hund rule. Hund rule say when we fill the orbital, for example S, P, D, F, the first option we fill the one time the same spin, because for example if I want for this one, I will explain I want to draw oxygen for example. Okay, 1s2 is a 2 electron. Okay, 2s2 is a 2 electron. But for the 2p4, first I have to fill 1, 2, 3. Okay, and Hund say we can the last electron we can come here. But if I draw here like this, okay, 2 in first 2 and in the second, it is wrong. It's not acceptable. It is a Hund rule because of the level of the energy. First, it must be the same and same spin, and then it can change. And we have also building a principle. It shows the subshell energy, how the electron feel up to electron, and increase the order of energy. Okay, for example, from the first layers, then second layer, and the third layer. The most important rule from this principal quantum number, angular and the magnetic and distant quantum numbers, it is the Pauli rule. Pauli said that we cannot find 2 electrons with the same 4 quantum number. It must be at least one of them must be different. It is very important, and it is very easy, and I can mention about this. And this rule is we can see in the periodic table very easily. For every element we can have these 4 quantum numbers, and in the next lecture I will speak about the periodic table.